Imagine you're trying to find a single word in a massive 1,000-page printed dictionary. Or maybe you're trying to sort a huge, messy stack of playing cards. You're definitely not going to scan front to back, right? No way. You're going to split that book in half, and then in half again. Welcome back to the third installment of our How Algorithms Actually Think series. In this explainer, we're taking that exact intuitive human strategy and formalizing it into literally one of the most powerful paradigms in all of computer science: divide and conquer. Okay, let's take a quick look at our roadmap for today. We're going to cover the intuitive strategy, the divide, conquer, and combine steps, real-world applications, clearing up some common misconceptions, and finally, why this pattern actually matters. All right, let's jump right into section 1, the intuitive strategy, or basically, human problem solving. You know, it's super easy to get intimidated by computer science jargon, but complex algorithms are actually just formalized versions of things we do naturally every single day. When you split that dictionary in half to find a word, or cut a deck of cards to sort it, you are intuitively dividing a massive problem into much smaller, manageable pieces until you land exactly on the right answer. It's really that simple.
And honestly, that intuitive dictionary strategy is the perfect bridge to our earlier explainers on recursion and backtracking. If you remember those, you'll totally see why framing divide and conquer is the absolute next logical step in computational thinking. We're essentially taking that repetitive, self-referential superpower of recursion and applying a very specific strategic structure to it so we can solve huge problems efficiently.
Moving on to section 2, divide, conquer, and combine, the core explanation.
So here is the formal blueprint of divide and conquer, broken down into 3 distinct logical pillars. First up, divide. This is where you take your original problem and break it down into smaller, similar subproblems. Second is conquer. You solve each of these smaller subproblems independently, usually by recursively dividing them further until they're so small they become a trivial base case. And finally, combine. You take the solutions to those tiny subproblems and merge them right back together to form the final answer to your original massive problem.
Now take a look at this. It brilliantly illustrates the continuous motion of a large problem branching downward, kind of like a tree. Notice how the top green node splits into manageable pieces, branching downward and shrinking in size. That's your divide and conquer phases in action. Then you see those pink and orange nodes. That shows those tiny solutions sliding back upward, merging perfectly layer by layer, until you hit that final bottom node, the complete combined solution to the whole shebang.
Let's look at the primary visual example of this in the wild. Merge sort. Picture an unsorted array of numbers. Merge sort basically takes a cleaver to that array, dividing it right down the middle, again and again until every single number is just sitting in its own isolated sublist of 1. And hey, at that point, a list of 1 is technically sorted. Then, the combine phase kicks in. It smoothly merges those individual blocks back together, comparing them step by step, ensuring every new combined list is sorted until the entire original array is reconstructed in perfect order. But merge sort isn't the only player in the game. Divide and conquer is a broad strategy, not just a single algorithm. Take Quicksort, for example. Instead of blindly having an array, Quicksort intelligently picks a specific element, called a pivot. It then partitions all the other elements, moving everything smaller than the pivot to the left and everything larger over to the right. Then it recursively sorts those two sides. So it's a completely different mechanical approach to the divide step, but it uses that exact same divide and conquer philosophy. So why on earth do we go through all this splitting and merging? Well, it's because of the incredible efficiency it creates, mathematically represented as O of n log n. Now, without getting bogged down in heavy math, the intuitive efficiency here is that when you cut a problem in half, and then in half again and again, the problem shrinks exponentially faster than if you were just dealing with it one single item at a time. This logarithm-driven shrinking is exactly what allows algorithms to handle huge data sets without slowing down to a total crawl. Next up, section 3, real-world software applications. And guys, this isn't just whiteboard theory. This exact logic is running inside the software you use every single day. Nearly every programming language out there, like Python or Java, heavily relies on divide and conquer for their standard built-in sorting libraries. And when massive tech companies process terabytes of data, they split those huge data sets into manageable chunks across thousands of servers, solve them independently, and merge the results. Honestly, it's the only real way to handle large-scale information efficiently. All right, moving to section 4, clearing up common misconceptions. Let's bust some myths. To get a crystal clear understanding of this paradigm, we really need to address its boundaries. First off, a lot of people think, oh, divide and conquer is just recursion. Well, actually, not quite. While it heavily uses recursion as the engine, divide and conquer is the whole vehicle. It specifically requires that exact divide and combine structural framework. Another huge myth is that it's universally the fastest approach. It just isn't. For problems with overlapping subproblems, things like dynamic programming or greedy algorithms are actually going to be way better suited.
Also, because merge sort and quicksort are the two most famous examples, people constantly assume they're basically the same thing. But look at the fundamental difference here. Merge sort divides blindly and evenly. All the heavy computation happens during the combine phase. Quicksort is the exact opposite. It does all the heavy lifting during the divide phase when it's partitioning around that pivot. By the time it hits the bottom, combining them is pretty much trivial.
Finally, let's look at Section 5, why this pattern matters. When you zoom out, this pattern actually underlies the essential functions of modern computing. We've already talked about efficient sorting with merge and quicksort, but it's also the absolute backbone of searching, like the binary search you probably use to quickly find elements in a sorted array. It even powers highly advanced mathematics under the hood, things like Strassen's matrix multiplication or Karat-Suba's algorithm for the super fast multiplication of incredibly large binary strings.
But you know, beyond just writing code, divide and conquer is a brilliant universal problem-solving philosophy. It serves as an incredibly useful mental model. When you're faced with a massive, overwhelming real-world problem, this paradigm trains you to recognize exactly how to break it into small, independent, solvable pieces, conquer those individually, and cleanly stitch them back together for the final win. So take a look at the massive tasks in your own life, or maybe your next big coding project. What overwhelming problem will you break down next? Just remember to divide, conquer, and combine. Well, this wraps up the third piece of our How Algorithms Actually Think series. If you haven't seen our previous explainers on recursion and backtracking, definitely go check those out to see where this all started. Thank you for watching the Tech Canvas. Complex ideas, clear pictures. Follow for more.